Here we have a two-variable function and a unit vector. You should check that this is indeed a unit vector. If you square the first and square the second and add them up, you'll get 1. So it's indeed a unit vector. But the interesting thing is, not only you're being asked to find the first derivative in that direction, but also the second derivative in that direction. So in other words, this is trying to measure the concavity in this specific direction. So how do you do that? Well, we always make use of the formula that the directional derivative is same thing as the gradient of f dotted with the unit vector, where the gradient of f is defined as all the partial derivatives. Okay? And we just have to use this formula twice and we'll be done. So let's see how that works. First, the gradient of f would be you take the derivative of x squared y by x, which means you just consider y as a constant multiple. Then all you have to do is differentiate x squared by x, which gives you 2x, right? And constant multiples just get multiplied without any change. And if you differentiate this by y, x squared is now considered as a constant, and therefore differentiating by y gives you 1, which just gives you x squared. So directional derivative of f would be 2xy x squared dotted with this vector negative 1/2 radical 3 over 2. Okay. Now what? What is this? This is dot product is component-wise multiplication, and you add. So 2xy times negative 1/2 plus x squared times radical 3 over 2, which is 2 and 2 cancel, so you get negative xy plus radical 3 over 2 times x squared. Okay, so that's your new function. That's actually the directional derivative, and I want to name this as capital F because now I have to differentiate this yet again using du, right? So I'm calling this as f, so now all I have to do is do the same procedure again. So we take the gradient of big F, which is you differentiate this by x. That means treating y as a constant, so that gives you negative y because x differentiates to 1, and x squared differentiates to 2x, so it's radical 3 over 2 times 2x. That's the derivative in terms of x. Now then I have to differentiate this by y. In that case, partial derivative with respect to y considered x as a constant, so although this looks really complicated, it's a constant, and therefore its derivative is 0 when you differentiate by y. So the only thing that you have left after differentiating negative xy by y becomes 1, and you get just negative x. Okay, and therefore the directional derivative of this big F would be this gradient dotted with, again, our vector u, in which case 2 cancels and it's component-wise multiplication, so negative y plus radical 3x times negative 1/2 plus negative x times radical 3 over 2, and that gives you positive 1/2 y, negative radical 3 over 2x, and minus radical 3 over 2x. And since these are like terms, if you add, these get doubled, canceling the denominator too, and therefore the final answer is 1/2 y minus radical 3x. Okay, so that's the answer. Just a little more word about what this is used for. So this is our final answer, right? This is the result of two derivatives, and that means note that means the second derivative, so this applied twice to the f, at, say, 1, 1, is, if you plug in 1 and 1, would be 1/2 times 1 minus radical 3 times 1, and that's going to give you 1/2 minus radical 3, and that's negative. And if the second derivative is negative, we know that second derivative negative means you have a frowning face, so it's an upside down parabola, or the concavity is upside down. So so f is concave down at 1, 1. That's a conclusion that you can draw, but not all directions. In the direction negative 1/2 radical 3 over 2. Now, this doesn't guarantee that it will stay concave down if you chose another direction. If you wanted to do something like second derivative test to see the concavity in all directions, then you have to do this for all vectors u, and that's the subject of this second derivative test in multivariable functions. Okay, so that's where these kind of calculations get used.